taking raw data, encoding it into a set of plain ASCII characters, and if the resulting encoding is not a multiple of 4 bytes, then it will pad that data with equals characters to make it a multiple of 4 bytes. So you can end up with anywhere from 1 to 3 equal signs, or 0 if the encoded data is already a multiple of 4 bytes. So I've just chosen to look for 2 equals characters at the end of this UDP packet. Incidentally, you might say, well, why use a PCRE for this? Because PCRE is kind of expensive, and that's of course true. But unfortunately, byte jump does not work at the transport layer header, so I can't make it take the length field of the UDP header and use that as an operator to get to the end of the packet data. So using this PCRE expression with this $sign allows me to do the same thing, but it's a slightly more expensive operation just because I have to appeal to the PCRE library. If somebody knows how to write a snort signature to look for the last byte and test that byte for a particular value, but not require looking at the header at the same time, please let me know. Maybe there's a way to do it. Okay, so that's the first thing. So base64 encoding is used by all FWNOP packets sent by the client. But we can do a little bit better than that. An artifact of the crypt CBC module is that it tries to maintain parity with the how OpenSSL encrypts data. So there's this static string, salted _ that's typically used in the encrypted data, and when that's base64 encoded, it shows up as this nice 10-character string, UTF, SD, etc. And so, as I was looking at a bunch of SVA packets, I saw, wow, there's this sort of invariant section right at the beginning. What the heck is that? I wasn't expecting that, considering that every single SPA packet includes 16 bytes of random data right at the beginning. But that was being generated, by the encryption algorithm itself. And so, looking for that for any pre-1.9.6 version of FWNOP, you can write a snort rule that would have a good chance of detecting SPA traffic this way. So here's an example of the raw encrypted the raw encrypted data for an SPA packet. You can see that salted string right up there at the beginning. And here's the base64 encoded version of that packet with that string in the base64 encoded form of it. There's no trailing equals characters in this particular case because the encoded information was exactly a multiple of 4, so it didn't need it. So we can also do a similar technique for GNU PG encrypted data. If you look at the magic database used by the file command, you'll see that it infers that any file that begins with hex 8502 corresponds to data that's been encrypted with GNU PG, and the base64 encoded version of that is this nice HQ string. I've also included a D-size requirement of greater than 1,000 bytes because once you start to use GNU PG keys, the SPA packets typically are a little bit larger, so they're usually over about 1,000 bytes. I use a 2048-bit key myself. And here is a sort of abbreviated version of what that packet looks like. It begins with HQ, and in this case ends also with the trailing equal sign because the original data was 1,043 bytes long, but it had to make it 1,044 bytes long to be a multiple of 4. Okay, so it turns out that it's easy to sort of stop this, remove these invariant sections. Yes, question? So the question was, would there be any MTU size problems with having such a large application layer payload? I've done a lot of traveling, and so far I have yet to encounter a network that does not handle that well. I mean, your typical MTU size on an Ethernet network is not going to be a problem. There are other network data link layer protocols too that could become involved, but I have yet to see that become a problem. So typically no. So the 1.9.6 version of FWNOP takes these invariant sections, it strips them out completely before sending the packet data out on the wire. The server side then says, okay, I've got this now totally random looking blob of hex or ASCII data, and it adds those invariant sections back in before attempting to do its basic for decoding or decrypting for Rindall packets or GNU PG packets, and therefore those snort rules now become ineffective against this latest release of FWNOP. Also, there are sort of, I would say, comprehensive port randomization features now within FWNOP, and this applies both to the destination port of the SPA packet itself, as well as the port that you choose to make your SSH connection over. So if you want FWNOP to create a randomly designated port that's port forwarded to your SSH server, you can do that as well, and that applies both to local connections to the local system, as well as forwarded connections to internal SSH servers that are not otherwise accessible. And if I can get this demo to work, I should show you an example of that. So just a slide on what I mean here. Here's the top command line that you should use with FWNOP. I want access, let's assume I'm on a routable network somewhere. I want access to this internal 192.168.10.22 server. In particular, I want access to SSH on that server. But I'm going to randomize both the destination port for the SPA packet as well as the port that I want to connect to SSH over. In this case, FWNOP assigns me port 3394, which I will use on the SSH command line to make the connection. So, not that port randomization really makes things difficult to analyze. It's just an additional, it raises the bar just a little bit more. I can't always assume that my connections are going to go over TCP port 22 for SSH. FWNOP can make that unpredictable. Okay, so let's talk about an attack against SPA. This one, I think, was particularly elegant. Came out 2 years ago, 2006. It's featured in a master's degree written by Sébastien Jean-Couillet. I'm sorry if I'm mispronouncing your name. Basically, the FWNOP daemon had no notion of maintaining a timestamp on incoming SPA packets. So an attacker that possessed an inline device to an SPA packet could intercept one, store it off on disk somewhere, let's say, and the client side, well, it sent this SPA packet across, but of course, SPA is never acknowledged, so when the follow-on SSH connection was attempted, it wasn't allowed. Well, the client probably just realized, oh, well, maybe my packet got lost somewhere or whatever. So the client sends a new SPA packet, which is now different. The attacker says, oh, that's okay, I'll let this one through. And then the server side would open up port 22, and the client would have no way to know that the original SPA packet that was seen was intercepted. The daemon side, the FWNOP daemon side, was unable to see that original SPA packet, so there's no way it could do a SHA-256 comparison against a new SPA packet to detect a replay attack, which means that if, at the same time, the client used -S on the command line to force the FWNOP daemon to trust the source IP on the in the IP header, the attacker could retransmit that SPA packet payload from a different source IP and gain the same level of access as the original attempt. Elegant attack. FWNOP is no longer vulnerable. It encodes the source address that you want access to within the encrypted data itself, and it maintains a timestamp for all incoming SPA packets. But if you know of another exploit against the SPA architecture, I'd love to have some feedback from the community about the architecture, so please let me know. Let's see, running short on time here. So this is the 1.9.6 release. There are a few additional things. In trying to write both client-side and server-side software like this, I've come to realize that a test suite is really, really important. And there is now test suite support for port knocking mode as well as SPA mode, of course. I think there's about 180 tests in there or something like that. But anyway, was there a question? Yeah, okay. Upcoming developments, I mentioned before, it's being rewritten in C. I was hoping to try to get that done by this conference, but just couldn't quite finish it. But it will be ported to OpenWRT as well as Packet Protector and other embedded distributions. It'd be nice to have some additional UI support in Java. This next to the last one here is, I think, kind of interesting. Now that FWNOP supports the interface to building port forwarding and NAT rules, I'm also going to add support for SPA proxying. So you can essentially build up chains of NAT rules to a deeply buried SSH server somewhere. And with FWNOP instances at each hop, and it will build those rules automatically so that you can access, from any routable network, all the way down in. Yes, question.
Yeah, that new proxy capability that you have, is that going to be leg by leg as you nest inside to an internal network, or are you going to have internal information encoded in the original SPA?
Yeah, so the question is, in that new proxy mode support, is the information encoded leg by leg, or is the original packet sent all the way through to the internal system? Yeah. So this is I'm still a little bit in the design phase for this particular feature, but a couple things are clear. Each hop in the SPA path has to be able to. So if I send the original SPA packet all the way through, that's fine, but each hop also has to have necessary key information to verify that it's a valid packet. At each hop, I could generate a new SPA packet with the same original information, with the exception of, let's say, the random number that's included in the data. It's still being worked out a little bit. I mean, there's some details there that we can talk about offline if you'd like. Thanks for the question. Okay. Okay, demo time, or keep going through some examples? What do you guys want? Demo, okay. This may take me a little bit to set up here because I wanted to show some specific information. Resolution. The question was, a lot of the stuff won't work for a stateful firewall. It actually depends. And of course, a stateful firewall is the most sort of nice way of using this because it keeps your connection live, whereas shutting the original accept rule down. But FWNOP supports client-derived timeouts. So if you want if you want the firewall to accept your SSH connection for 5 days, you can do that. If you configure the server to allow that. Yeah, the question was, it won't work for something like a Cisco or PIX, or getting packets through. The basic requirement is that a UDP packet to the whatever destination port the client designates is sent through at some point and monitored by an FWNOP instance. So, there's some details there, but it should work typically.
Just another observation. It seems that
yes.
the facilities with the latest release are in place to go into supporting a UDP hole punching method behind the authorized
The question was the support in the new FWNOP 1.9.6 release was designed to use a UDP hole punching method in conjunction with TCP connections, or I'm not quite sure.
I mean, it would be a UDP tunnel, in other words.
Yeah, the access. So once the UDP packet is sent by FWNOP, actually you can send it over TCP or ICMP2. But if it's a UDP packet, FWNOP daemon monitors that packet. The access that is requested, whether that is a TCP port access or UDP port access, that's encoded in the packet itself by the client. So I'm going to try to demo this. What's that? Oh, make this bigger. Okay. Actually, here. Is that better? Can you see that? Okay, so just a quick mention of the architecture here. There are two systems involved here, the two separate systems down here where I have the cursor down here. This